All right, guys, can you hear me again?
Yes.
All righty. What are you guys thinking? Do we have any questions about what we had on the slides before the break? What is it that is going to save the day here? How can this possibly be made to work out? I mean, in general, this should not be possible. What is it that is going to save the day here? The thing that's going to save the day is that here you have F0 and over here you have F1. Is there a connection between F0 and F1?
Is that the P tilde?
What about the P tilde?
S0 equal, I mean, S1 equal to the expected value.
Yes. This here was exactly the expected value of F1 of S1 under the tilde probabilities. And what was that equal to? And then we discount, right? We also need to have 1 plus R here. So we discount here. And then what do we get here is P tilde F1 S0 times U times 1 minus P tilde times F1 S0 times D. So this is the key thing that's going to make this work. Because what happens is if you take this expression, then you can take 1 plus R here over on the other side. But then I'm going to get the first term here. I'm going to get the first term here. And so what would it be? I take this stuff, I plug them in here. What would it be? So it'll be 1 plus R goes over there. So that's the same thing as here. So I need the stuff inside the parentheses. Here I need P tilde times F1 S0 U plus 1 minus P tilde times F1 S0 D. That's that term, and the same thing down here. This is P tilde F1 S0 U plus 1 minus P tilde F1 S0 D. Now it looks a lot more promising, right? Because these two over here, they also appear over here. So should we try to do it and see if we get the same expression, no matter which delta we solve for? So we could do it here on a piece of paper, or we could be a little bit more lazy and go over to Mathematica. I like the last one. So what is it we want to solve? Can you all see my Mathematica screen here? Can you guys all see my Mathematica screen here?
Yeah, we can see.
Okay, so let's try to solve these two equations. So the first one was, so I want to solve, and then what was it? P tilde times F1 evaluated at S0 times U. Let me know if I make a mistake here, because if I make a mistake, it won't work. And then over here, you'll have 1 minus P tilde times F1 times D. And then you'll have plus delta, this is our unknown, times S0 times, and then is U minus 1 minus R. I want this to be equal to F1 S0 times U. I want to solve this for delta naught. I get this long, messy expression. Let's just double check that it looks more or less correct. Yeah, if anybody sees a typo, let me know. And then we'll solve the similar equation. Solve the similar equation. And the difference is going to be, over, these terms here will be the same because they're related to the money market account. Then over here, there'll be a difference. There'll be a D here, and there'll be a D over here. Right, so I can solve these ones too. And then I can ask, are these two the same? So I can say full simplify. Are these two here the same? And it doesn't look like it, right? It doesn't look like this at all. But you see there's a parameter in here, PT. So if I go ahead and I solve and I let PT vary, here comes the miracle, right? If I want this thing to be true, PT has to have that form. Is that true? Well, this is our infamous risk neutral probabilities, right? So even though it looked like a hopeless thing to try, we just got it to work. And the reason we got it to work was simply because there's a link between F0 and F1. Are there any questions about what we saw here? So this consistency here is, these are the same. This is a key aspect. The other key thing was the formula for P tilde. Or was it 1 plus R minus D divided by U minus D? So these two things here, they allow us to have consistency between these two equations. And that's the entire key. So this is how you get, so now you have X naught, then you have delta naught. So to get the generic one, so you get delta n by solving. What would it have to be? It would be on the right hand side. You would have Fn plus 1 times Sn plus 1, and so we want this to be Xn plus 1, and you want to write this out as Xn plus delta Xn plus 1. So you have to solve this thing here, and then you'll work it out just as before. You have this long mess, 1 plus R, it will be Xn plus, and then it will be the thing that you're hunting, the delta n. And then over here you have Sn plus 1 minus 1 plus R, Sn. And this thing is going to come out to be Fn plus 1, and then you have Sn times Sin plus 1. And so on. And so you're again going to get two equations in the two unknowns. You'll have it in Xn, and you'll have it in delta n. But Xn, well, what it's going to be is Fn of Sn. All right, so you really have two equations and only delta, so you need consistency. And this is similar to before, right? And this is the way that you do it. You create this sequence of delta n's by solving these equations here, and they all involve these functions that you created in the first step. All right, any questions on this part? If not, I propose that we look at an example where we try to make this a little bit more like tangible, I think is a good word, to make it a little bit more real, perhaps. And I had a problem prepared. This is another old exam problem from last year and the year before. This problem here, problem number 6. Okay, so problem number 6, I'm just going to write down the key aspects again. So we have an interest rate, which is equal to 0. And then we have U's and D's. So because the interest rate is equal to 0, the interest rate is equal to 0. So the U's and the D's, you have to have this relationship. So I'll have 1 is bigger than D, less than 1, less than U. R is equal to 0. Okay, so we got those. The filtration is the one that's generated by the stock, equivalently the one that's generated by the first endpoint flips. So the first question says, calculate this conditional expectation where you square the stock. Okay, so this would amount, for us, this would amount to computing Fn. Right, so the payoff would be this Sn plus 1, this would be that square function, and then we compute the conditional expectation of it the period before. So find this function G that satisfies this property, and the formula for P is exactly what we're used to when the interest rate is equal to 0. Okay, so that would be the first step. So let's try to do that. So let's try to do this. So calculate the conditional expectation of Sn plus 1 squared given Fn. And how will we go about doing it? Well, we'll follow the usual recipe that, I mean, Fn, this is the sigma algebra generated by the first n coin flips. Sn here, this is Sn times psi n plus 1. And so we're going to use that the first part, is measurable. And we're going to use that the second part is independent. So very similar structure to the calculation we've done before, and let's try to work it out. So we get the conditional expectation to be Sn squared psi n plus 1 squared given the sigma algebra generated by the first n coin flips. And so what we'll use now is what we use a bunch of times, that the first part here is measurable, so we can move him outside. And then the second part will be independent, so we just take the unconditional expectation. So this equality sign here uses 2 parts. It uses that Sn is measurable, and it uses that psi n plus 1 is independent of the first variables. Then we're almost home free, because what we have now is Sn squared times this expectation. So this is Sn squared times, what we get will be P tilde times U squared plus 1 minus P tilde. Don't square the P tildes, right? It's P tilde times this thing here squared. This is a D squared. So our function, so E tilde Sn plus 1 squared given that sigma algebra. This is G of Sn for G of X simply just being x squared p tilde u squared 1 minus p tilde d squared. Any questions about this part? So the second part of the problem is related to the consistency of these two equations that that we just talked about. Let me try to bring it up one more time, and we can see it. So we're looking at problem 6, the second part. It's asking us to find delta n. So we have this property. Okay, so we want to look at, so this here was part A. Part B, part 2. We want to find delta n such that xn plus 1 is equal to Sn plus 1 squared. And let's try to work that out. How are we going to do it? Well, we'll proceed according to the same thing that we just did. I'm on the left-hand side. On the left-hand side, I'll write this as xn plus delta xn plus 1. But this is the same thing as Sn squared psi n plus 1 squared. I will then plug in what this here is, and now keep in mind the interest rate is 0, so I'll get here that this is xn plus, and it's just going to be delta n times Sn plus 1 minus Sn. It's a bit simpler. This step here uses that r is 0. There's an assumption made in the problem that r is 0. And it simplifies this equation here. And so we want this to be Sn squared psi n plus 1 squared. Sn here is as before. This is the same, saying that xn plus, and then you have delta n, put Sn outside, you get psi n plus 1 minus 1. That you want this to be Sn squared psi n plus 1 squared. So as before, you really have two equations and two unknowns. But this is the same. This here is the same as saying this is the same as saying that xn plus delta n is n, and then you have a u minus 1, and this is Sn squared times u squared. And the same thing for the down. That this is equal to Sn squared t squared. So seemingly you have two equations and two unknown. You will solve, and then you should verify. You should check that your xn is exactly equal to that g that we had from up here. That g we had right there. You should check that xn is equal to g of Sn. Solve and check. Any questions on this part? Any questions on this part? You guys got very quiet after the break. We had lots of questions before the break. Are we good on this part here after the break?
Yeah, I think I just got a review because it went kind of fast towards the end of the other part.
At the end of the other part, which is the question asked you. The question asked you, so we have you're given that Sn plus 1 is given in terms of the previous one as the usual way in these binomial models. And what you're being asked to do is to calculate the conditional expectation. We could have done a bunch of other things. We could have done stuff like another example could be instead of 2, we could have had could have done a square, say. Instead of a square, we could have done. We could also have looked at stuff like e tilde of Sn Sn square root, say. Like, say that you were being asked to calculate what is this equal to. So what we're doing here is we're going backward recursively. What we're doing is we're going to say that, well, I can write this. I can write this thing here as an expectation where I'm conditioning inside, right? I know that the conditional expectation has the property that if I take the expectation of it, I'm going to get the correct expectation. So I can write this here as the expectation of a conditional expectation. So I'll go back iteratively. One step at a time. Like I'm working in this direction. And I'm hoping up to end up here. And this will tell me what the value is in here times 0. Okay, so I can put in anything I want here. So let me put in all the conflicts except the last one. So I go 1 period. And the payoff I'm getting out here, this is like a square root of Sn. Like, how do I move this payoff to times 0? Well, I set up a replicating portfolio and figure out what the initial value of this replicating portfolio is. And the initial value is going to be this expectation here. So let's try to compute it. This is e tilde. But this thing that you're finding in here, in our notation from before, this thing here would be Fn minus 1 of Sn minus 1. This was the notation we had before. This one here, this would be our F0 of S0. So we go one step back at a time. I take the conditional expectation. How would I work it out? Well, I will use the property that we talked about before. It's a square root. So I'll have Sn minus 1 here, psi n. And then condition. And then condition, and then we will now use the properties from before that the first part here is a square root, right? So the square root of a product is equal to the product of the square roots. So the first part here can be pulled outside the conditional expectation. So I'll have it out here. And then that second part, that has nothing to do with the coin flip. So I just take unconditional expectation. So I'm left with this. This step here, this step uses that Sn minus 1 is measurable with respect to the first n minus 1 coin flips. It uses that, and it uses that psi n is independent of all these coin flips. So that's this equality sign. And now I can work out what the inner expectation is. This here, this is a constant, and it's going to be equal to p tilde times, this one can be the u or d, so this is going to be a square root of u plus 1 minus p tilde, and the square root of d. Right, don't take the square roots of p and 1 minus p, just take the square root of u and take the square root of d. So this expectation here, it allowed us to go from here to here, and the value that we're getting is p tilde square root u plus 1 minus p tilde square root of d times the expectation times the expectation of the square root of s n minus 1. So it allowed us to go one back. So now we can go one more back. I can do the same trick again. I can write this here as p tilde square root of u plus 1 minus p tilde square root of d times, and then the expectation. Now I want to go from here. I want to go one further back. How will I do it? I'll put in the conditional expectation here. Now what I want to condition on is one fewer, because I have moved one period over. Any guesses on what I'm ultimately going to end up with here?
So you will have
The same thing. The same thing, right? The same thing, just put a square here. And then e tilde square root of Sn minus 2. And then I can keep doing this. Ultimately, I'm going to be left here with p tilde square root of u times 1 minus p tilde square root of d, but then to the power probably an n here, and then a square root of s0. And so that's the value. That's the value that you get out of here. This question mark, this is equal to this mess down here. This is going to be square root of s0 times p tilde square root of u plus 1 minus p tilde square root of d, everything to the power n. Like the value in this binomial model of getting the payoff square root of the stock at time capital N, the value of that payoff at time 0 has this formula. And that's the price of a derivative that pays out the square root of the stock. Did that help? Are there questions on this sheet here? Are there any questions on this part here, guys? I cannot read your mind. So in particular, when we're not even in the same room. So if there's something here that is not clear to you, you've got to ask me, and then I'll try to go over it again. Is there something here that you want me to talk about again? Okay. Then there's one more thing that's left, and I just want to make sure that this is in your homework. So I don't even think it's in your homework. Okay, so the last part that I want to say a few words about is the Markov property. Just a few words about the Markov property. So the Markov property of a let me call them something here. We use the word M for martingale, X for wealth. Let me call them Y maybe. So the Markov property says the following. It says that if I compute the conditional expectation, so this is Markov. If for any function f, the conditional expectation, the function applied to the Markov process, this is Markov if for any function, when I apply it here, computed, that this is really just going to be, right, and so inside here, inside f, for us, we will very typically have these coin flips here. This will be psi 1 up to psi n. But in general, this is going to be a function of all these coin flips, but it's Markov if this thing here is really just a function g of yn alone. So in general, this conditional expectation, this would be, in general, this would be a function, so let's call it capital G of psi 1 up to psi n. And it's Markov if you only have to keep track of the last one. So there are a number of processes that are Markov. So for example, the stock price, Sn itself, is Markov. And this is Markov. This is under both P and P tilde. So to prove that, we need to take a function and calculate the conditional expectations. Let's do it under P tilde because this is where we're going to be using it. So it's computed under P tilde. So you take your function, an arbitrary function, any function that you want, you plug it in here, you take Sn plus 1, and you condition on all the previous coin flips. Okay, we go through the motion again, that's what we had before. We need to prove that this here is only a function, this is only a function of the current stock price. I don't have to keep track of all the coin flips. So I'll write this here out as an expectation of f of Sn and then psi n plus 1 given the previous coin flips. And then we'll use the independence lemma that we have used so many times before. Use the independence lemma. So when you need something with the Markov property, you basically always have to use the independence lemma. And what it says is that you take out what is known and you take the average over the rest. So what you end up with here is a P tilde times f of Sn, and then this will be a U plus 1 minus P tilde f and then Sn d. And this is your function. This here is equal to g of Sn, where g of x is p tilde f x u plus 1 minus p tilde f x d. Right, so that's Markov. I only have to keep track of the current value of the stock. Any questions on this calculation? What we did here is very similar to what we've been doing all day. So what is an example of something that is not Markov? Well, an example of something that is not Markov, you need to be a little bit more elaborate. And the example that is given in the textbook, and this is also at some point going to appear on your homework, is to look at the max. So you're looking at, and this is important for like look backs. This is important for certain options, is to look at the running max. The running max process. So if I look at, say, mn, this is going to be the maximum. This is going to be the maximum of the previous stock process. So this is S0, S1, up to Sn. This is the running max. And this here has applications in, for example, in pricing of lookbacks. If you want to have a more specific application, we're just going to be using it here. And so I could ask here, is this a Markov process? Is this Markov? Well, so is Mn a Markov process? Right, and the answer is no, it's not true. And so what we want to do is to test for it, right? You will be taking a function and you will be applying it to m at time n plus 1. You'll be conditioning on the first n coin flips. Okay, so far so good. And then the next thing that you do, is you plug in what m is. So this is equal to f, and then the max. Okay, so the max, how do we calculate the max? We need to relate it somehow. Mn plus 1, I have to relate it to what we had before. So how would I do that? Well, I would say that the max is going to be up to time n plus 1 is going to be equal to the max up to time n, and then the stock price at time n plus 1. Like that maximum here up to time n plus 1 is equal to the maximum of the time n, and then the current value. Okay, so we have that one in there, and then we condition. So I also need to have, independence. This thing here is not independent. This one here is measurable. So I need more work here. To use the independence lemma, I need these two quantities to be independent, and they are not. So I need to massage this a little bit more to get independence. And the way that I'm going to do it is to look at the ratio, right, divided and multiplied by the same thing. So no big deal. This is going to be the same. Right, and what I have here, that ratio, this ratio here, this is my psi n plus 1, and that one is independent, and this one here is measurable. So I can now use the independence lemma as before. This is the independence lemma once again. This is the independence lemma. I'm going to end up here with E, so that expectation has to be calculated. We need to decide on what to measure we under. Let's put it under the risk neutral, so let's put tildes everywhere. then what I'm getting here is p tilde, the function that I'm computing the conditional expectation after it gets applied to the max, the running max, and then inside here I'll have the maximum. Here I'll have mn. Then my side, this is the independent one. That's the one I take average over. This is going to be u times Sn. That was the first part. And then plus 1 minus p tilde. And then my f, and then apply to the maximum mn. And then instead of u, now it's in d times Sn. And for this to be Markovian, I have to be able to write this as a function g of mn. But that's not possible. This here is not a function of g of mn because I have an s here. This here is a function of mn as well as Sn. So mn is not Markov. Because when you computed the conditional expectation up here, what came out was the random variable mn and the random variable Sn. And it's not enough just to know what the running max is. You also need to know what the stock price is. So you will not just have a function applied to mn, you will need a function that is applied to both mn and Sn. So therefore mn is not a Markov process. The benefit of these Markov processes is that you can see here in general, as you move out with more and more coin flips, but you're gonna have to keep track of more and more stuff here. But this is these functions here, right? It's gonna keep growing. Like you're gonna have a bigger and bigger and bigger domain. What the Markov structure allows us to do is to keep the domain fixed. No matter how many periods you're looking at, you just have to keep track of either m or m, and in this case, it's going to be m and Sn. So this is the benefit of identifying this Markov structure. But that number of functions you have to keep track of does not depend upon how many periods you have in your model, in particular in continuous time. In continuous time, right, you have to keep track of a full path here. There will be uncountably many you have to keep track of. Whereas if it's a Markov structure, you just have to keep track of one. Okay, this is all I had in mind for today. We looked at, today was pretty heavy on theory. I recognize that, but yeah, we had to get it done. This part here is this is really the meat of the course. And are there any questions before we say goodbye?
Thank you, Professor.
Right, so next time, this is the last lecture we will have before your all exams 2 weeks from now. So if there are things that you want me to talk about during that lecture, you're welcome to send me an email and I'll try to see if I have something that I can talk about. Otherwise, we're going to be doing some more examples next time. Try to talk about some of the things that I have seen last year in the all exams that we should try to avoid this year. Okay. If you haven't signed up for a time slot, please do so. If you have signed up, just double check that I didn't mess up the online schedule, that it looks the way that you would like it to look. If not, there are office hours as usual later this week. And if not, I'll see you on Tuesday.
Thank you.
You're welcome, guys. I'll see you later.